Kia ora all. Thank you for joining us tonight. I'll just run through a few of the IRC team so you know who's on board. Firstly, we have Gavin Palmer, the General Manager of Operations. We have Anita Dorr, General Manager of Policy and Science. We have Jean-Luc Payan, Manager of Natural Hazards. We have Joe Gaylor, Manager of Communications and Marketing. We have Tim Van Verden, who you would have met, Natural Hazards Analyst. Frederic Gulcher, Team Leader, Communications and Media. We have some members of the Civil Defence Emergency Management team. And myself, I'm David Cooper, Principal Advisor, E-Relationships and Strategic Stakeholders. We have with us Councillor Alexa Forbes, and she'll be doing a short introduction shortly. We also have some technical experts, Sean Van Balagoy of Tonkin and Taylor Limited, and Matthew Gardner of Land River Sea Consulting. And Jean-Luc will expand upon their role and what they're presenting shortly. So I'll just pass to Councillor Forbes just to do a quick introduction and karakia.
Kia ora koutou, no mai haere mai, koutou katoa ki tēnei hui, ko Alexa Forbes tōku ingoa. Welcome everyone, I'm Alexa Forbes, one of your ORC councillors, and I'll just want to open us up with a karakia and then go through what we're doing tonight and then hand back to David for introductions and the person that actually knows what's going on. So, whakataka te hau ki te uru, whakataka te hau ki te taonga, kia makina kina te uta, kia matarātara ki taie, ehi ake ana te atakura, hei tio, hei huka, hei hauhu, tihei mauri ora. Now, I'm thinking that most of you or all of you will know about this project, which we've been undergoing for a couple of years now. It's about understanding the natural hazards inherent in the landscape of this area and working through adaptation planning. And as you'll know, or most likely know, ORC took ground samples from the town late last year and commissioned new flood hazard and geotechnical investigations that are now complete. We thank you for attending this evening, and the purpose is to report back to you the findings of those investigations, and the people that are doing that are highly qualified to do so. But we'll pass back to David now. He will tell you more about that. Thank you, David.
Kia ora, Councillor Forbes. So just to run through some logistics, if you could please use the chat for the questions, just until we get to a certain point in the presentations where we're going to have a more verbal Q&A. That's not to shut you down at all. And as you send through the questions, I will record them and ask them of the presenters at various points. It is just to keep those presentations rolling, and some of the questions may be asked by the presentation further on in that presentation. So please just use the chat in the interim to ask any questions or make any comments. Please don't hesitate to ask questions. I know some of these areas can be a wee bit intimidating, but it's really important you understand that no question is a bad question. And if you're thinking of a question, I can guarantee there'll be 2 or 3 others who are thinking of the same question. So please jump in. If you have any issues or you don't want to have the question attributed to you, you can send the message to me directly, but really encourage you to put it out in the open. Please mute your mics. You can inadvertently have some noises going on in the background, and to get the presentation rolling, if you could please mute your mics. So what we're going to do is I'll pass over to Jean-Luc, who many of you will know. He'll run through, provide background on the technical presentations and introduce our experts. And then as we go through, we'll stop at various points just to ask some questions. Jean-Luc.
Thank you, David. I'm just going to share my screen, David, and let me know if you can see it.
Yes, it's up there, Jean-Luc.
Okay, thank you. So I think you've lost the screen, have you?
Yes, yep, it's dropped off.
Okay, I'll try again.
It's up there now, Jean-Luc.
Okay, thank you. So thanks, hi everyone. So I'm Jean-Luc, I'm the manager of the Natural Hazards team at the Regional Council. I've been working at the Regional Council since 2008. And my role and the role of the Natural Hazards team is really to investigate natural hazard in the region and help assist lead adaptation when required. And I work with Tim Van Moorden. He's a natural hazard analyst in the team, very involved in the head of the lake adaptation work. So what's the program tonight? So I have a 5 minutes overview of what the head of the lake adaptation strategy work is about. But really the focus of tonight will be about two very fresh reports that were produced by the first one by Tonkin and Taylor on liquefaction hazard at Glenorchy, and the second one on flood hazard that was produced by Land, River and Sea Consulting. So the first report was completed by Tonkin and Taylor, and the work was led by Sjoerd van Ballegoy. So I'm just going to stop sharing quickly my screen. Just 1 second. So Sjoerd is a senior geotechnical engineer at Tonkin and Taylor. He has been extensively involved in liquefaction studies, investigation following the 2010 and 2011 earthquake in Christchurch and the 2016 Kaikoura earthquakes. One of his roles was to map liquefaction and lateral spreading damages and the effect on residential building. He also helped developing the rebuild strategy for the New Zealand government. So Sjoerd has authored over 100 reviewed journal papers and covering proceedings on liquefaction, lateral spreading and ground improvement. So Sjoerd has led the works that you'll be hearing about, and we're very fortunate that Sjoerd is available to respond to questions tonight also. And the flood hazard study was led by Matthew Gardner. So Matthew is a river engineer, specialized in water resources and modeling. He's a director of Land, River, Sea Consulting, and he has been working in that field since 2006. He's carried very detailed hydraulic modeling for major rivers in New Zealand and floodplains, including in Canterbury on the west coast, in Marlborough, and in the Wellington and Wairarapa region. So it's got high knowledge of braided rivers and modeling those rivers. And yeah, Matt has led the investigation and the flood hazard study for the Dart and Reese floodplain. Just reshare my screen. So the two studies, and most of you are aware of that, are part of a wider program of work with the objective that you have on the slide here. But I think the word I want to highlight tonight is resilience. So the purpose of that adaptation work the Regional Council is doing is about building resilience. And that's a reflection of the Otago Regional Council community outcome that is described in the Otago Regional Council long-term plan. So one of the outcomes is about ensuring communities are resilient in face of climate change and natural hazards. And the work we are doing, and we've been doing since 2019, is about that, is about understanding the physical environment, understanding what are the changes, either related to the floodplain or to climate, and what we can do about them. The approach we've taken is to consider all the hazards, and we want to have a holistic approach in adaptation. So not only into one type of options, but we want to consider all the options available and how to combine them in the best way. How are we going to do that? With using the Ministry for the Environment guidelines about adaptation and a framework or an approach called Adaptation Pathways. So I want you to focus on that circle first. Don't worry about the text for the moment. Focus on that 10 steps circle. So that's an illustration of the adaptation approach that we are using for the head of the lake adaptation strategy. So the approach is really based on 5 questions. The first one is what's happening. It's understanding what the physical environment is, what are the future changes, what we can expect in the future. The second question is what matters most? What matters for the community? What do you value in the area? What you want, what you like? But also understand what is exposed, how those changes, how those natural hazards are going to affect values and infrastructure in the area. The third question is about what we can do about those changes and making sure values are considered. And the last 2 steps is about implementing the findings. So implementing the plan and making sure the plan is working and adapting the plan and back again into that cycle. So the big advantage of that approach is really the ability to make decision and provide certainty when we don't really know for sure how the future is going to change. We know changes are happening, but we're not, at this stage, we don't know how fast or when things will start to change. What this approach helps to do is put a plan together and adapt the plan while the changes are happening. One thing I want you to focus on is that it's at the middle of that cycle. We've got community engagement, and that's in the middle because it's central to all those questions. So that's a commitment that we had right from the start of the project, is to work with the community, with you, on a no surprise basis. And what this means is when we know about something, we share it with you as soon as we know it. And that's why we're here tonight, is to hear about the findings of those 2 natural hazard studies that were just completed. Now, if you focus on the wider text, that's really to illustrate the work that's been completed by the Regional Council since 2019. And it's really been focusing on those 2 first questions, what's happening and what matters most. And you can see that those last 2 studies are really fitting into those 2 questions. The purpose of that work, and especially those 2 studies that we will hear about tonight, is to guide the next part, which is what we can do about it. So tonight is about the findings, but later on, we'll be continue working with you and the rest of the community around what we can do about the changes that we know are very likely to occur in the area. So it's not the first time that liquefaction work or flood hazard investigation are completed in the head of the lake or for Glenorchy. You're very aware of similar studies that's been done in the past. But what is new here, if we take the liquefaction, is the fact that it's a very detailed on-the-ground investigation. So we had Tonkin and Taylor doing subsurface geotechnical investigation and taking that to a scale that is quite refined compared to previous studies, and Short will be detailing that just after my talk. What's new with the flood hazard study is the level of information we've got now about the flood hazard characteristics. So not only where the flooding would happen, but also how deep and how fast the water will be in some part of Glenorchy. So we've used a very detailed hydraulic modeling to do that, and Matt's going to explain how this has been done and what are the findings around that. But the other thing we've done is trying to include the changes in the river that you probably remember hearing about a year ago when Professor James Bressington presented to the community about those changes and how basically the reef and that floodplain have been changing in the past and are expected to change in the future. And both findings, the finding of both studies are going to inform decision-making around adaptation. So tonight is really to hear about those studies from the expert. We've got Shord and Matt available to present the finding, but more importantly, here to respond to your questions about what they've done and what the findings are. But we've got other things also happening. Next week, we will be presenting the 2 reports to the ORC Data Information Committee. And you'll be able to hear the presentation and discussion on YouTube. So if you go on the ORC webpage, you'll find the link to the YouTube page, and you've got it also at the bottom of my slide here. So that'll be an opportunity for councillors to discuss those findings and ask questions. And very importantly, late in June, we are planning to have follow-up meetings in person in Glenorchy to discuss those findings and have your feedback. That'd be another opportunity for you once you've had time to think about this information. That'd be another opportunity for you to ask questions or give us feedback. Now, just 2 other things to have in mind. If you want to keep in touch or give us feedback, we've got a specific email address, headofthelake@orc.govt.nz. So you can send us an email there if you have any questions or you want someone to contact you, you need a report, feel free to use that email address. And we've got a dedicated webpage where you find tonight's presentation from tomorrow, previous report, previous presentation, if you need to access that, or if you want to give that to someone else that was not able to come tonight. So I will hand over to Shord now, and I'll thank you everyone for coming.
Okay, good evening, everyone, and kia ora. Can everyone see my screen and hear me? Okay, great. So I'm going to talk about the liquefaction vulnerability assessment that we have undertaken for the township of Glenorchy. And I'll just acknowledge some of my co-workers there. The work has also been peer reviewed by a colleague from WEN Specific Geotechnical Engineers. Right, so liquefaction is a little bit of a different hazard compared to one that we're more familiar with and see on the news more regularly, such as flooding. We're more familiar than what that is. So I'm just going to spend a few slides, a little bit of time just explaining what liquefaction is, the hazard, how and when it occurs before we then start looking at Glenorchy. So the liquefaction hazard, how does it occur? Well, we need 3 key elements for liquefaction to occur. We need the right soils. Sandy soils are the right type of soils that can liquefy. They have to be loose. So very dense material doesn't liquefy, rock doesn't liquefy, clays don't liquefy, so it needs to be specific soils. The second ingredient is that they need to be saturated. So if we've got groundwater, shallow groundwater, such that the soil is submerged, then that's another key ingredient. And then the third key ingredient for liquefaction to occur will be a sufficient level of ground shaking. And that is both a combination of the duration of shaking intensity from an earthquake, the duration as well as the intensity. So what is liquefaction then? Liquefaction is something that happens below the ground. So I've got the diagram on the left-hand side shows the process of liquefaction. The red circles that you see are the sand grains. The blue in between the sand grains is the water. When the shaking occurs, during the shaking, all of the soil particles start to mix up and pack closer together. And after the earthquake, you can see the particles they are packed closer together in a tighter and a denser format. What that means is the water needs to squeeze out as a result of that process, and that water squeezes out to the ground surface, and the ground surface goes down. You could do this experiment yourself. If you have a bowl of sugar, fill up the bowl with sugar, and then start tapping the side of the bowl, and you'll see the level of the sugar go down a little bit. And that's exactly the same as what can happen with sand. Now, when that process occurs, we then sort of get a manifestation. So before the earthquake shaking, we'll have a non-liquefying crust that is of material that's not likely to liquefy because it's above the groundwater table. And then below that is the layers of soil that could liquefy. During or immediately after the earthquake, the earthquakes cause that to densify, the layer that liquefies. A lot of groundwater comes out, gets squeezed out, and then through fissures and cracks in the ground starts coming up to the ground surface, welling out of the ground surface, and a lot of sand erodes with it, producing a lot of sand boils, and the ground surface goes down. And in the areas where the liquefaction is quite bad, significant quantities of water and sediment come out of the ground, as shown in the photo below, which is a typical photo in some of the worst affected areas in Christchurch. And that can cause a lot of damage. So rather than showing lots of diagrams, I thought that I'd show a little video that you get a sort of an idea. Now, this is a video taken after the Christchurch earthquake on the 22nd of February 2011. And this is what happened for the 2 hours following the earthquake shaking. I'll just pause it there. After 2 hours, there was a sort of 1 to 2 feet of water and sand covering the entire streets. The ground surface had gone down a lot, lots of damage to the houses, the buried infrastructure, the roads, etc. So what are the consequences of liquefaction? And so this is a nice diagram that shows what can happen before the earth, what the sort of built environment might look like before the earthquake and then after the earthquake. One of the first consequences of liquefaction is differential settlement. That's where the ground settles unevenly, and that causes damage to buildings, buried pipes and roads. And so I'll just take you through a few photo examples. When the ground surface goes down unevenly, houses settle unevenly. And you can see in the picture here, the house is tilted in one direction and the garage is tilted in another direction. Some houses tilt, other houses sag through the center, but all types of nasty damage occurs to houses when the ground goes down unevenly. Another consequence of liquefaction is that heavy objects sink into the ground, such as buildings or power transformers, or heavy objects such as cars or power poles. And so here are some photos. So, when the ground loses strength from the earthquake shaking, and it is temporary, the strength is regained, but immediately after the earthquake, while the strength is lost, heavy objects can sink into the ground. There's an example of a power pole sinking into the ground. There's examples of heavier houses sinking into the ground. These are some of my colleagues. They are not that tall. This is where the house was designed well to withstand the shaking damage, but was just not built in a way to be able to manage the the loss of strength of the ground. And so while undamaged from the shaking that occurred, sank into the ground. And here's a photo from Japan following the Nagata earthquake. And for larger buildings that are quite heavy objects, the ground can just give way and things can even topple over. The toppling here of these buildings is not from earthquake shaking, it's from a loss of support from the ground itself as a result of liquefaction. Not only do heavy objects sink, but light objects float. Light objects are objects that may become buoyant, like underground fuel tanks, underground pump stations, manholes from sewer and stormwater systems. And so here is just some photos that I took in Christchurch of a underground pump station that started to pop out of the ground as a result of the liquefaction. What that results in is the electricity cables got severed off, the pipes severed off, and so the water supply was completely cut. So even if the pipes themselves, in undamaged areas of Christchurch might have been okay, if the pump stations are inoperable, no one's got water. And you can see the picture on the bottom there of a manhole, a sewer manhole that's popped out of the ground. You can imagine the pipes are still where they are, and so the manholes come up and the pipes have now been severed off. And those, at that break, a lot of liquefied sand material entered those pipes and for kilometers backfilled those pipes. That then solidified, and so it's a very big repair bill, not only just to repair that manhole, but kilometers and kilometers of pipes needed to be dug up, because you just couldn't unblock them. Now, near lake edges or river edges, when the ground loses strength, the ground can laterally spread, as shown in the diagram below. And that will cause a stretching and a cracking of the ground. And so as a consequence, near sort of lake edges, buildings and underground pipes and cables and roads are pulled apart. And so here are just some photos. This is a place in Kaikoura next to Lyle Creek following the Kaikoura earthquake. And you see an entire garden right next to a creek starting to laterally spread into the creek. Fortunately, that lateral spreading didn't extend all the way back into the footprint of the house, but there were some houses that were not so fortunate. Here are some pictures of houses in Christchurch, and where we can see the lateral spreading that's occurring, tearing the houses apart. And of particular note is the photo on the bottom right, that not only does it cause a horizontal stretching, but we also see the vertical stepping going down. Now, the timber frame houses are were stretched, but if that lateral spreading had been bigger, some of those walls may have been pulled out and may no longer have been able to adequately support the structure, and we would have been seeing more examples of building collapses. Fortunately, we didn't in Christchurch, but that's because the lateral spreading was only of a limited extent. If the lateral spreading had been bigger, we would have seen some significant issues. And while it is very difficult to sort of capture photos of damaged pipes, one would only need to sort of be a little bit of imaginative to think about the main services, the pipes, the electricity cables, that are all running through this main arterial roadway. If this ground has been sort of spreading and cracking and moving towards the river, what the condition of those pipes and cables would be: completely damaged, stretched, broken. Bridges, they then sort of tend to compress. Now, that the final the consequence of liquefaction, and lateral spreading, which is often overlooked, is the significant ground surface subsidence that can occur. We saw in Christchurch 0.5 metre to 1 metre of ground surface subsidence, making low areas even more flood prone. And in areas where a lot of lateral spreading can occur, that ground surface subsidence can even be larger. Here's a picture of a vineyard in the Waiau Plains, out of the Waiau River, downstream of Blenheim, towards the coast. This entire area liquefied and slumped and spread into the river. Now, you can see the extensive cracking there, and you can see all of these vines that are underwater. They used to be high and dry, like the rest of the vines. But when this liquefied and lateral spread, that area dropped by 1 to 1.5 meters. This is not a river that's in flood. This is the ordinary mid-tide level. So you can see here that there's a significant drop. Now, fortunately, this was just an area that was only planted in vines. Not very nice for this farmer who, with what happened to their land, but it could have been worse if this area would have been covered with houses. In Christchurch, near all the rivers, around the Avon River, we also can show this drop. The cross-section profiles that I'm showing here, the light grey shows the floodplain levels before the earthquake with the profile of the river, and the black line shows the profile post the earthquake. And so we can see the considerable drop that has occurred, about 1 metre of drop. The land adjacent to the Avon River and many of these suburbs surrounding the Avon River was at about 2 metres above mean sea level. As a result of the earthquakes, now the suburbs are 1 metre above mean sea level, or basically at the same level as the high tide level. And during king tides, these areas now become submerged. This is an area that never used to have stop banks, but as a result of the earthquakes and the significant ground surface subsidence, stop banks have had to be built to keep out the king tides. So low areas became even lower and more flood prone. Now, the liquefaction is not just something unique that's happened to Christchurch following the 2010 to 2011 Canterbury earthquakes. Liquefactions also occurred in Kaikoura following the 2016 Kaikoura earthquake, as well as in Blenheim. Liquefaction was observed in areas in Napier following the 1931 earthquake. It was observed in the Bay of Plenty extensively following the 1987 Edgecombe earthquake. And it's occurred on the west coast as well as a result of the 1929 Murchison earthquake, 1968 Ngahua earthquake, as well as some smaller earthquakes. So it's not just unique to Christchurch. And so we've now done a detailed study in Glenorchy looking at the subsurface conditions, and we're found that this hazard can occur in Glenorchy as well. So just going through the 3 key ingredients, and I'll sort of step through now and specifically in Glenorchy, what we've done. So from the 10th to the 16th of October, we did extensive subsurface investigations throughout the township of Glenorchy, and that's denoted by the triangles where we've pushed cone penetration tests into the ground. That's pushing a steel rod into the ground to measure the resistance. The easier it is to push the rod into the ground, or the less force that we need, the looser that the soils are, the higher the force that we need, the more pressure that is needed to push the rods into the ground, the denser the soils are. So that gives us an idea of how dense or loose the soils are. And then we also drilled machine boreholes and got core out of the ground, and we were able to see what the types of soil that were there. And indeed, we found that most of the soil underneath Glenorchy is cohesionless material that is predominantly sandy. It's got some silt in it, but it's quite sandy, and it got some gravels mixed in with it as well. Now, as we started to look at all of that subsurface investigation data and look at the process of how that's built, there are quite distinct layers there. There is a deposition of material lower down that looks to have come from the Buckler Burn and sort of deposited while the lake levels were higher, tens of thousands of years ago, and has formed underwater quite loosely. Then, as the lake levels dropped, material from the Buckler Burn has continued to deposit there, and formed a bit of a slightly denser material on top. And then as the lake levels have dropped further, the delta has become dry, and then we've had debris flow deposits over the top, but predominantly now the Buckler Burn is depositing its sediment into the lake, forming a new delta there. So the delta that we've got, or what the township of Glenorchy is built from, is the sediment that's been deposited by the Buckler Burn. And it's only in the recent history that the Reese river deposits have come to butt up against the delta formed by the Buckler Burn. The lake used to wrap around, but the Reese has been steadily advancing with the sediment coming down from the Reese. These soils are the soils that are prone to liquefaction. So we have the first ingredient, and it's not just a couple of meters of soil that could liquefy. We've found that the soils are to depths greater than 20 meters are the soils that could liquefy. So considerably thicker than the depth of liquefaction susceptible soils that typically occur in Christchurch, which are really only the upper 10 meters of soil that could liquefy. So in Glenorchy, we're finding that the thickness of susceptible material is double that typically what we've seen in Christchurch. The second part, or the second ingredient, is groundwater. Now, we know where the lake levels are, we know where the lagoon levels are, and then using the groundwater monitoring wells, we've been able to develop a groundwater model, contour plan of looking at how the groundwater levels, what they are throughout the Glenorchy area. We see that they sort of start at the lake level and they gradually increase by a metre or two from the lake level up to the back end to the lagoon level. So there is a gentle flow of water, or a gradient, starting at sort of the inland part, driving towards the lake. It's a very consistent. And so if we then take the ground surface elevation that we've been able to obtain from the LiDAR surveys that have been undertaken, and we subtract that from the groundwater elevation, we can get a depth to groundwater. And so we see that the groundwater is shallowest at the sort of northern end and the western end of Glenorchy, and it's deepest right up against the Bible Terrace. So we've got deeper groundwater there. So Glenorchy has groundwater, it's shallow, and obviously the shallower it is, the worse that it will make the liquefaction hazard. And finally, we've looked at the earthquake shaking. Now, Glenorchy is in a seismically active area in New Zealand. The whole Southern Alps of New Zealand is seismically active. And so from the codes and the building codes and practice modules and NZTA bridge manual, we've been able to get the different seismicities at the different return period levels of earthquake shaking. But we've also looked specifically at the shaking from an Alpine fault event. Now, the Alpine fault event has ruptured ruptures on quite a frequent basis, typically once a 300 years, or approximately every 300 years. Sometimes it's ruptured a bit sooner. I think the shortest reoccurrence interval has been sort of gap between earthquakes on the Alpine fault's been 150 years. Sometimes it's been longer. at 575 years, I think, is the longest that has ruptured, but on average it ruptures every 300 years. Now, the Alpine fault last ruptured in 1717. So there's been 305 years elapsed since the last rupture. That's not to say that an earthquake is going to happen tomorrow, but we know that on average it's rupturing every 300 years. It's sometimes been a bit longer, sometimes a bit shorter. So the probability of an earthquake on the Alpine fault, given that it's been quite a long time ago since it last ruptured, is now effectively a 75% chance of occurrence in the next 50 years. So something that's quite likely over our lifetimes. And so we've done a specific assessment of what the liquefaction and lateral spreading will be for an Alpine fault rupture as well as at the different return period levels of shaking. The shaking levels themselves are high enough, particularly at the higher return periods, for liquefaction to be triggered. So unfortunately, all three ingredients are present. So how do we then do with the liquefaction assessment? We take these subsurface soil investigations that we have done, these CPT tip resistances. On the horizontal axis is the amount of force or pressure that needed to be applied to push these probes into the ground. And on the vertical axis is the depth below the ground surface. And what we can see is a denser material near the surface where it was a bit harder to push the probe through. Once we broke through that at about 5 meters below the ground surface, we found that there was very little resistance to these probes being pushed through the ground, indicating quite loose soils below about 5 meters depth. We can then take these soil strengths, plot them on this graph here, and the horizontal axis on this graph sort of represents soil strength, and this comes from case history data from around the world, and then on the vertical axis we get earthquake strength. So this is a plot of soil strength versus earthquake strength. When we plot in the green area, those are the soil layers that are not predicted to liquefy for a given level of earthquake shaking. When we plot in the red area, that's when we sort of expect liquefaction to occur. And if we're in the yellow and orange areas, it's a little bit uncertain as to whether or not liquefaction may occur. So what I'm now showing on the right-hand screen is just profiles of slices of earth below the Glenorchy, sort of 3 different sort of test results. And at different levels of shaking, from 1 in 25 year right through to 1 in 100 year, we've then sort of showing the results of that assessment. The red layers then are the layers that are predicted to liquefy. The green layers are the layers that we don't expect to liquefy. And so it's quite clear from this assessment that there's a very thick layer of soil that's expected to liquefy at earthquake shaking, starting at about 1 in 100 year levels of shaking. Now, there is some uncertainty in the shaking levels, and so we have looked at those uncertainties. And so for a lower bound case, liquefaction triggering starts at 1 in 100 year levels of shaking. And in an upper bound case, allowing for uncertainties, it's sort of more towards the 1 in 25 years. So, but, by the time we're looking at 1 in 500 year events, significant, thickness of liquefaction is predicted. When we've specifically looked at an Alpine fault event, the unique thing about an Alpine fault is it will be a lot longer in duration. It will be a magnitude 8, so the duration of shaking will be considerably longer. So even though the intensity of the shaking intensity might be lower, the duration will be a lot longer. And when we take that into account, levels of liquefaction comparable to the 1 in 100 to 1 in sort of 500 year levels of shaking are expected for an Alpine fault scenario. The upper 20 to 25 meters of soil is expected to liquefy for most of the Glenorchy Township. And that will therefore have some consequences. So I just showed for a few test locations. And so this map here shows for an Alpine fault rupture event with the typical shaking that would be expected in Glenorchy from such an event. The different dots represent the different locations where we've done testing in Glenorchy, subsurface investigations. And then the colours denote the thickness of liquefaction that's predicted to liquefy for an alpine fault rupture event. And so orange would be 10 to 15 metres of soil that's predicted to liquefy, and then the red would be 15 to 25. So the most likely case of shaking from an alpine fault event would cause quite a bit of liquefaction to occur within the Glenorchy area. If the shaking is worse than what was typically expected, then it'd be a bit worse, the liquefaction. If the shaking is a bit lower, then there might not be much liquefaction at all, apart from at the lake end. Each fault rupture is different, so we just need to. No earthquakes are the same. Sometimes earthquakes cause higher levels of shaking, sometimes they cause lower levels of shaking, and so this just does reflect some of that uncertainty. But the most likely case is quite extensive liquefaction. So what we need to do is start thinking, okay, what does it mean when we've got 8 metres of soil that liquefies? Is that going to be a problem? Well, that depends. It depends on how thick the non-liquefying crust is on top. It depends on how thick the liquefying layers are. It depends on how loose they are. And so there is an index that we can calculate, which is a liquefaction severity number, which sort of predicts the chance of liquefaction ejecta occurring and a lot of land damage. So when we calculate an index number with a value of 0 to 8, the liquefaction may happen at depth, but there's really not a lot of damage at the ground surface. So small index numbers are no damage. If we're calculating index values, LSN numbers greater than 25, we're really expecting high to severe land damage, as we're sort of indicating in the picture there. So for the alpine fault scenario, if we then take into account what's the thickness of the soil layers that are expected to liquefy, what does that then mean? What we sort of show is that, typically for an alpine fault, high to severe liquefaction, so a lot of sand coming out, a lot of differential settlement, and the damage that I've shown in the associated pictures occurring through most of the Glenorchy area, but the hazard does decrease a bit, as we sort of come up, in the sort of southeastern side, right up against the Bible Terrace. And that is mainly because the depth to groundwater starts to become a lot deeper in that location, and also because the soil conditions are a lot denser. There's a lot thicker capping layer of denser material there. Now, bathymetric surveys have shown that the sort of lake level, that there is quite a drop-off. The sort of height, about 50 meters out from the lake edge, is the lake sort of bottom is fairly shallow, and there's just slowly gets deeper, comes to about the sort of brown line, and then there's a steep drop off. That drop off is about a 25 meter drop off over a 100 meter distance. And this drop off creates a free face. So when this liquefies, that could then allow lateral spreading. Now that height or that drop off in Glenorchy, or in the lake adjacent to Glenorchy, is about 5 times greater or 5 times higher than the drop off in the areas where lateral spreading occurred in Christchurch and Blenheim next to the Avon River. So the Avon River is typically 4 to 5 meters deep, or the banks, and estuaries, there was about a 4 to 5 meter height difference. Here we've got a 25 meter height difference. So there's a considerably greater height that could then allow for more lateral spreading compared to what we've seen in the worst areas from Christchurch and Blenheim. Different models have been used to try and assess the lateral spreading. It is one of the most difficult things to model and predict. So we've used different methods to assess the lateral spreading. And all the methods are pointing to generally 3 to 4 meters of lateral spreading is predicted sort of near the lake edge. And then decreasing or distance back from the lake, that lateral spreading then decreases. So that's a considerably large lateral spread. That level of lateral spreading, the 3 to 4 meters, is typically 2 times worse than the worst observed lateral spreading in the Christchurch residential red zone. So just trying to put something in perspective here, that the lateral spreading hazard in Glenorchy is 2 times worse than the worst damage that we observed in Christchurch. So what do we do with this information then? So we've taken all of this information and then put it into damage zones. Now, these damage zones, we've based it on the MB and the Ministry of Business, Innovation and Employment and Ministry for the Environment guidelines. And effectively, there is a sort of a clear criteria on what to do. So we've got national consistency on how we are zoning these areas. Now, these are damage zones. These guidelines were developed for the consideration of the liquefaction hazard for rezoning for development of greenland. So the idea, greenfield land. So undeveloped land, when it was being considered for zoning changes, for land development, that's what these guidelines were developed for. And so, what was anticipated there is that sort of future development, in different areas of New Zealand, would ideally be undertaken in areas with very low to low liquefaction vulnerability. They're trying to sort of, avoid putting new developments in areas with high hazard. In the areas with high liquefaction vulnerability, the guidelines, point to that these areas with high liquefaction vulnerability should either be avoided, or that there's area-wide ground improvements undertaken before houses are built on top. Or alternatively, houses could be built within those areas, but they would require more robust foundation systems to withstand the effects from higher liquefaction vulnerability. In the areas with major lateral spread damage, and a severe lateral spread damage, near the areas of the lake edge where a lot of lateral spreading is expected, those areas, the guidelines clearly sort of, say avoid these areas unless the lateral spread hazard can be mitigated. But in the case of Glenorchy, the ground conditions, the liquefaction, the soils are so deep that trying to mitigate the lateral spreading by ground improvement is not practical. So the guidelines sort of say future development in such areas should be avoided, left as greenfield. However, the Glenorchy is already an existing town and it's not a greenfield area, so there's no guidance available what to do for different hazard zones for existing developed areas. So we've had a look at what can be done in these areas, if they are already built on. And so, given that Glenorchy is already sort of a developed area, Section 1.22 of the Canterbury Recovery Residential Guidelines provides guidance for building designs for various levels of lateral spread damage vulnerability. And for major lateral spread damage zones, there are some heavy duty foundation options available for residential new builds in such areas. But they are very expensive. They add about $50,000 to $100,000 extra cost over and above the cost of a standard residential house on conventional foundations to deal with the damage or the major lateral spread hazard. For the severe lateral spread damage zones, where the lateral spread is very severe near the lake edge, there are no off-the-shelf solutions, and more substantial engineering works would be required, which are outside the scope of any guidance and would require specific design. Existing residential buildings cannot be expected to safely withstand those levels of lateral spread, and so any new builds would need very heavy duty engineering. And on top of that, very significant vertical ground surface subsidence would occur. So any foundation works would only be to for a life safety, to protect the structure, protect the occupants in a structure. it wouldn't actually avoid subsequent damage from a vertical drop. So here are those zones as we pull all this information together, with the sort of blue area being a low liquefaction vulnerability, sort of the orange being a medium, and a high, and then we've got those lateral spread zones there. We're just sort of an indication. So that's what basically the study is finding. Now, I must point out that these lines are not sort of an exact position. There is uncertainty, and we have denoted them as wavy lines. So one shouldn't sort of look at this and go, my property falls inside or outside of this line, but need to sort of see the general trend of what this look like with the different zones. Obviously, the further away you are from a river, you're outside of the influence of the lateral spread. But these are the different damage zones, and obviously now need to sort of consider, well, what does this mean, and the next steps will obviously be what do we do with this information. But so far this has been just looking at, well, what is the hazard. So that concludes my presentation. I presume that there will be questions afterwards, and that we'll do the flood one next, but I'm happy to take questions up, whatever's you prefer.
Thanks, Stuart. I think we have got a few questions coming through. We might stop at this point because I know a lot of these community members, I recognise a few of the names, are very well informed. So we've got some questions coming through that I might ask of you now.
Yeah.
The first is coming from Bob, who's asked, how do we compare with the Queenstown CBD? And I'm assuming that's both in terms of risk and potential damage against those various scenarios.
Okay. Well, firstly, we've not done any study for the Queenstown CBD, so I'm not completely familiar with all the soils that are there. I haven't personally done Queenstown studies. I know a little bit from talking with colleagues who have done projects there, that there are some different soils. Depths to rock are different. The levels of seismicity, they're just another 40 kilometres further away from the Alpine fault, shaking. So the levels of shaking are a bit lower. Groundwater levels are different. There is liquefaction hazard there, but I'm just not sure of the extent and the severity. And so, I can't answer all those questions. But this is a very active environment. Groundwater is shallow. There's high shaking intensities. So this area is probably worse, but I'm not been involved in detailed studies of Queenstown, so it's difficult to compare at this stage without data.
Thanks, Stuart. And I should have said right at the start, please, anyone who isn't familiar with the chat function on Zoom, please scroll right down to the bottom of the Zoom screen. You'll find a chat button right at the bottom. So you just click that and type into the wee screen that pops up to the right. If you have any issues, please just yell out. So we've got another question here from Michael W. On the liquefaction presentation, the top 5 meters or so was shown to be tougher, and my layman understanding from Christchurch examples is this can provide a raft that provides some protection. Do you have any thoughts or response to that, please, Jordan?
That's right. And maybe I'll just go back a few slides to show that. So with the example I took there, the top 5 meters at that particular test location were tougher and they're denser and therefore not likely to liquefy, providing a capping layer to the liquefaction beneath. The thicker that raft of non-liquefying material was, it does provide protection. But unfortunately, the thickness of the liquefying layers underneath is so thick and so deep that the thicker that liquefying layer is, the more of a raft or the more of a capping layer one would need. Now, that capping layer does vary in thickness throughout Glenorchy. The capping layer is thicker towards the south and is thinner near the lake edge and sort of, you know, the upper reaches, so that capping layer does vary. That's been taken into account, into consideration, but it's not just the thickness of the capping layer, it's the thickness of the capping layer relative to the thickness of the liquefying layers underneath. And so while the capping layer is a bit thicker throughout parts of Glenorchy compared to Christchurch, the thickness of the liquefying material is thicker as well. So, you know, there's a cancelling effect there. So, yeah, it has been taken into account, but it's unfortunately in many areas not enough, you know, to provide adequate protection.
Thanks, Jord. We've had a question here from John. It would be interesting to know what the expected ground level drop would be in an Alpine fault event. John, I think Jord may have covered that after you've answered the question, but if I'm wrong, please take yourself off mute and let me know.
No, I think that was answered. It's about a metre. I think it would be really useful to have a plan that shows where effectively what would be underwater in the township after an Alpine fault event.
Okay, so the higher levels of vertical drop will obviously be greatest near the lake edge where the lateral spreading will occur. As you go further back inland, there will still be vertical drop there, but you know, only as a result of the densification, not because of the added drop because of liquefaction. So there will be vertical drop, you know, in most areas. It'll be worst here and least, you know, least in the sort of the blue area.
Thanks, Jord. Nikki Gladding has asked a question. I think we might save that to the end, Nikki. I think it's more a process question of council staff and maybe a combination of process question with council staff and also experts. What we might do now, just to keep this kicking along, I'll pass to Jean-Luc, who will present the next presenter. Jean-Luc.
I think we can go directly to Matt because I've done the presentation in my talk.
Cool. Thanks, Jean-Luc. Over to you, Matt.
Sure thing. Tēnā koutou katoa. Nice to be speaking to you all tonight. 1 second, my screen has gone. Here we are. All right, I'm going to go quite quickly tonight because we have gone on a wee bit already, and I'm sure you've got things to be doing. But I can take plenty of questions at the end if needed. So basically, this evening I'm going to be summarising to you the flood modelling work which we have recently carried out on the Reese and the Dart rivers. So we've built what we call a 2D hydraulic model of both of the rivers, starting from the road bridges and heading down to the lake. And so the extent of the model is just shown on the screen by the red boundary. So the model, the key inputs into the model, the first input which we need is the terrain data, or so that we know the land elevations, and that's been based on LiDAR data, which was flown by the Otago firm Land Pro and was captured in 2019. So it's important to highlight that this is a fixed bed model, and what I mean by fixed bed is that it assumes that the gravels are not moving during the flood, whereas in reality we know that there's a lot of gravel transport occurs during a flood event. So the river is aggrading in some locations and scouring out in others. So these effects need to be manually accounted for, and that's one of the key aspects that the engineer needs to take account for. So we have two main inputs into the model. The first input is the flow model, which we call the upstream boundary conditions. So we have flow coming in both in the Reese and the Dart rivers. In this model, they're just being input at the road bridges. And then the key downstream boundary level, which we have, is the level for Lake Wakatipu. And so as we know, that level rises and drops over time and is obviously also heavily influenced by the flows coming into the lake. So the flow inputs in this model have been developed by hydrology staff from Otago Regional Council, And it should be pointed out that the hydrology for the Reese River in particular is quite complex, and we do have a lack of gauging information in the catchment. So the Otago Regional Council staff have developed quite a complex rainfall runoff model to find a relationship between the amount of rainfall falling onto the catchment and what that relates to in terms of flow. So we do have a flow gauge, a reliable flow gauge on the Dart River, but we haven't had a long-term flow gauge on the Reese River. So that's all based on modelling. And the final model can be used to output water level, depth, velocity. We can make hazard maps, and then we can also output a number of other parameters such as shear stress, which is just one parameter which can be used to help understand potential for erosion, for example. And again, I just want to highlight that a model is obviously only a tool, and it's a tool which we use to help understand the real world, but we must always interpret these models in light of limitations. So this is a model of a very dynamic, it's a riverbed which is constantly changing day to day. We've got vast amounts of gravel coming out of the upper catchment, and every time it rains, more material comes down, and that material gets moved around the floodplain. So it is difficult to get like a perfect representation of that system with a computer model, but what we do is we do our very best, and we get a model which is able to replicate historical events as best as possible. So here's just a visualization. Now Shord presented some screenshots which showed some of the LiDAR in his previous presentation, so we've all seen it before, but this just highlights the basic topography of the Glenorchy Township itself, with the Reese River coming in at the north of the screen. And so we just see the coloured legend there. So the dark purples are a higher elevation, and the oranges and yellows are a lower elevation. So as we can see, that Glenorchy is essentially built on quite a large fan, with the delta protruding towards that fan. So once we've built the model, the key thing we want to do is we generally calibrate a flood event. So I've written calibration here, but we would really call this validation, because we haven't got a large amount of measured water levels to calibrate against. And so what we do is we try and use anecdotal as well as photographic evidence in order to validate the reliability of the model. So we've got a number of flood photos. There are several videos available online of the flood event of February 2020, and we've also spoken to a number of landowners, possibly some of you who are listening in tonight, to get an understanding of what happened during the event, and what the extent of inundation was, particularly in Glenorchy. So because we had more information in Glenorchy itself, the focus of this model, of the model validation at least, has been for the township and the wider Glenorchy area. And so what I'm showing there on the screen is just a screenshot of our modelled simulation showing the peak flood extent for the February 2020 event. So the red line on the screen there is a line which we've drawn, which we believe was the actual flood extent. Now that's based on a combination of, examining photos and talking to some of the local residents. And as you can see, the blue is the modelled water level, and it gives a reasonably close representation as to what actually happened. And as I explained before, the inflows into the model are based on the Otago Regional Council predicted flows based on their rainfall runoff modelling, and the orange line just shows you where the existing Glenorchy stock bank is. So I'm just going to quickly show you a animation of the flood event. So this is the model in action. So the arrows show the direction of the flow, and the colours are an indication of depth. And so the bluey purple are shallower water, and the greens and the reds are deeper water in this example. And so you can see the river starts filling up. There's a lot of spilling in the Reese River, and once those lagoons fill up sufficiently, the stopbank overtops. And as occurred in February 2020, we get significant flooding along the base of that stop bank at least, and it just flows along that existing contour level out to the lake. So that was obviously on fast forward. So we had about 8 to 12 hours of flooding there occurring in a little bit less than a minute, but just to get the feel as to what the model is actually doing and what it's representing. So once we have once we've calibrated or validated, as I explained, the model, we're then able to have a degree of confidence that it will be suitable for predicting flood extents for future events. And so we've used the model to assess the potential impact for a range of flood events. And so what I'm showing here is what we call a flood hazard map. And so this map takes into account both the speed of the water as well as the depth, and it takes that combination of depth as well as water speed and puts it into a hazard category. So we've got categories from 1 to 6. So a hazard category 1 is generally safe for vehicles, people, and buildings. Hazard category 2, for example, is unsafe for small vehicles. But if we go up to a hazard category 6, it's unsafe for vehicles, vehicles and people, as well as all building types are considered vulnerable to failure. So that's the red category, which luckily for Glenorchy, there's only a few areas showing within the river channel itself, the lake, and within the lagoons where it gets significantly deep. The other areas are generally lower categories than that, but there are some areas which are quite significant hazard categories for what we would call a 100-year average return interval event. And here's just an example of how that hazard categorization is developed. And so you can see we've got the velocity on the x-axis, or the speed, as well as the depth on the y-axis. And so once we have a combination of depth and velocity, we pull that into the different hazard categories. So as many of you already know, I believe that James Brassington from the University of Canterbury has presented to you previously in regards to the constantly changing nature of the riverbed with the geomorphic changes with significant sediment coming in, and how the riverbed has been grading over time, causing it to be what we say super elevated, i.e. the bed level is relatively higher than the surrounding floodplain. And so we believe that there is significant risk for outbreaks to occur in the future. These outbreaks actually occurred already in the February 2020 event, and there is a risk for a permanent avulsion, or for the river to permanently change course. And we believe that based on the relative elevation of the surrounding land, that would quite likely, the Reese River in particular, would like to avulse towards Glenorchy. So we've tested the sensitivity of the flood extent to an avulsion. So to show you what we would expect to happen here. So what I've got on the screen is what we call a 1 in 100 year average return interval flood extent. And so the color categorization is based on depth. So this is a similar flood extent to what occurred in February 2020. It is a larger flood extent and deeper. And then if we had an avulsion heading towards the stop bank, this is what would occur. So I'll just go back to the previous one. So you can just see that portions of land, we've got these properties up here to the right of the image. You can see they move in from, so a lot of them are in that green category, which is 0.3 to 0.5 of a metre, and they move into that 0.5 to 1 metre. So if their floor levels weren't flooded, currently in a 100-year event, with an avulsion, they would likely flood. But apart from that, what we do find is that, well, the extent of flooding is twice it is greater. It's not significantly greater, and that's simply to do with that fan head which Glenorchy is built on, controlling the extent of flooding. And so here's just some arrows just to show the basic direction of flooding. So the stop bank is currently overtopped. It was overtopped in February 2020 and will overtop in similar sized events and larger events in the future. So we find a stop bank overtops for basically the entire length in a 100-year flood, but the main flooding comes out here by the lagoon, it fills this low-lying area, and then it works its way back around and just follows that natural topography and finds its path back out to the lake. And here's just again highlighting that natural topography. And that's why we're only seeing flooding in that part of town, because the rest of the town is built on a significantly higher elevation. The model's been tested for sensitivity to roughness of the land, like the size of the bed material, vegetation, other parameters which can affect the roughness, water levels in the lagoon. What we did find is that, well, actually it's not that sensitive to the water levels of the lagoon, because the sheer volume of water which is likely to come down the Reese River in a flood is significantly larger than the capacity of those lagoons in the first place. If they were relatively empty, they would fill up in quite a short period of time with the flow volumes which could come in, and therefore the flood extent in Glenorchy is not really altered. So here's just some screenshots. This is our estimation of a 100-year flood extent based on the current riverbed, acknowledging that the riverbed is a grading, so this will likely change over time. But we can see that this is the Kinloch road, the access road to Kinloch. So we can see that quite significant lengths of the road would likely be cut off during a flood. We have observed that velocities are sufficient. They would likely cause scour and damage to the road surface. We already did see significant erosion and scour to the road surface in the February 2020 event, so that does match with observations. But we would also expect to see access issues for a range of roads in the regions of Priory Road as well as Swamp Road, even parts of the Glenorchy Rootburn Road. So we would expect anyone living in the area would be stranded for a period of time. Interestingly, we find with lake levels, there are two types of floods within Glenorchy. Flooding, which you've all experienced from just a high lake level on its own, the 1999 one being the highest lake level we've got on record, as well as river flooding. So what we found, that a river flood combined with a very high lake level didn't necessarily have a significant impact. And again, that's just because we're controlled by the natural topography. So here's an image showing a river flood combined with a high lake level. So I'll just go back, and so that's a 100-year lake level combined with a 100-year river flood. And so you can see at the top end it's slightly deeper. It's about 100 mil deeper up in this area here. But we're finding that there's quite significant drop coming out to the lake. And so the main impact of the high lake level is it does slow the floodwaters down in this lower area, but of course it's significantly deeper. So whilst the hazard from velocity is slightly less, the hazard from depth is greater. So each one cancels each other out. And here's just an impact showing 100-year lake level is shown in yellow. So purely flooding from a lake level, high lake level alone is going to inundate very large areas of Glenorchy. And then once we combine that with a 100-year river event in the Reese River, we find that we do get an increase in flood inundation, mainly at this top area here, and then coming down past the golf course, etc. Slightly deeper, slightly greater extent as we come down closer to the lake, but realistically, the lake is what's controlling the flood extent in that situation. For climate change, we've only assessed the impact of climate change on peak flow. Impact on lake levels have not been investigated as part of this study. In reality, the impact of climate change on lake levels is very complex, and we're going to get a change in intensity of storms in the wider catchment, and change in climate in terms of changes to evaporation, transpiration, all these things, so we may get more evaporation, but at the same time we may get more rain. With more intense storms, we may get more erosion in the upper catchment, and therefore more sediment will come down into the rivers. Sediment in some of the rivers which drain the lake, such as the Kawaro. If the bed levels in the Kawaro were to rise, then potentially the lake level could rise. However, if there's ongoing maintenance and that gravel is cleared out, then it may not have much of an impact. So there's a lot of unknowns. It probably warrants study in future years by some experts in the area, but for now we've only considered impact on peak flow. And so impact of climate change, we've modelled what is considered a sort of an upper limit of potential climate change. Looking at the IPCC terminology, it's called an RCP 8.5 event, but it's looking at flow on its own. And what we find, so that flood extent there is the impact of a significant increase in flow. So we can see flood depths get deeper, and the flood extent increases to a degree. Here's a look in terms of hazard categorization rather than depth. So we just see some of the areas move up one hazard categorization, but the extent doesn't change too significantly. And here's just a look at the wider floodplain area. So this image, which I'm showing you here, is 100-year, and then we move into 100-year with future climate. So you can see the extent is fairly similar, slightly greater, but the depths are just increasing. So in summary, we've got significant flood hazards to Glenorchy in the wider area. However, particularly in Glenorchy town, it is confined by that natural fan head, so by the topography. The existing Glenorchy stop rank will not prevent flooding and is likely to overtop in the future, as seen in 2020. We would expect most of the access roads to be cut off during a large flood event. So you need to be ready to have sufficient supplies to get you through those events and have a plan in place for your household, because evacuation may not be possible. And we also found that in a high lake level event, the flood extent for Glenorchy at least would be dominated by the lake levels. We already know from previous studies that there's a significant risk of avulsion, and we found that an avulsion will increase the flood extent and cause that entire stop bank to be overwhelmed. Something I didn't mention up until now, but just we have investigated the impact of a breach on the stop bank, and we found because that stop bank is already being overtopped quite significantly, a stop bank breach doesn't have a significant impact on flood extent. It only impacts on the time of inundation. So if it did breach before it had overtopped, then we would expect the floodwaters to reach the properties earlier than would otherwise be the case. Highlighting that flood risk is not a static thing. Our modelling is based on the 2019 topography. However, it must be noted that the river is aggrading as more sediment comes in from the upper catchments. And the increased flows due to climate change are likely to increase the flood depths and velocities. However, the extent is largely controlled by topography. And just in terms of climate change, all we've looked at for this one is what would a 100-year flood extent, what would it become? But I guess we do also need to acknowledge that we're expecting flood events to become more frequent, as well as increasing in size. So that's everything I have. So happy to take, a little bit rushed, but happy to take questions from here.
Thanks, Matt. And apologies to everyone. I didn't leave enough time here to, we were meant to conclude at 7:30. Didn't leave enough time to get through some questions, but what I might do with your patience is we'll just extend the meeting by 5 to 10 minutes and get through some of these questions that are coming through. So a couple of questions. Nikki, I will get to your question shortly because it's what to do with process. In terms, and Michael asking a question, increasing the height of the existing bund protection, does that provide any significant benefit or reduction to the flooding given lake levels will coincidentally likely be high and circumvent the bund anyway? Question for you, I guess, Matt.
Yeah, sure. So yeah, it's a bit of a complex one about raising the bund. We would expect flooding to get around the back of that bund anyway. You'll be chasing your tail a little bit. The river is constantly rising. There could be some purely from a structural sense, some protection could be provided by raising that bund in in the short term, but as a note, if the lake is rising and if an avulsion was to occur, then it would have to be a pretty high bund to hold back an avulsion. As you increase the height of those stop banks, the risk of failure will increase, and the consequence of a failure will also increase. So if it was to fail, you would expect quite a significant volume of water to rush towards those towns. So it would have to be very carefully thought through.
Thank you, Matt. A question for you, Jean-Luc. Bob has asked, has ORC approached QLDC about raising the stop bank? The locals did 2 years ago, and the council have been sitting on their hands since. Is there anything that we can add to that discussion? Oh, you're on mute, Jean-Luc.
Thanks, David. The result of those studies have been shared with QLDC for them to consider. Now, as Matt indicated, raising the flood bank is not necessarily going to fix the flood hazard issue for Glenorchy for the long term. So that's something QLDC will have also to consider. And they've recently done a little bit of upgrade on the flood bank, mainly to protect the toe of the flood bank and just slightly raise some of the low spots, especially around the golf course area.
Thanks, Jean-Luc. Bob, you're asking some detailed questions around the bund. I'll let Matt, we may, instead of going into a deep dive on some of these technical questions, we might take them on board and include them in the frequently asked questions given the time we've got at hand. John Glover has asked, can you tell us a little bit about the brief for the Dam Watch study? Tim, do you want to grab that one?
Sure, yeah, thanks, David. So yeah, as we've mentioned previously, we've got a study underway at the moment, led by Dam Watch Engineering, and has input from others as well, including Matt and James Brasington, who you've seen work from before. And yeah, that's looking at what can be done in terms of mitigation or management of flooding or floodplain hazards, so both flooding and erosion, and looking at various areas on the floodplain, so the township and Lower Reese area, the Dart floodplain Kinloch Road area, and also further up the Reese around the Reese Bridge. So that's looking at primarily river management or engineering type approaches, looking at what might be technically feasible, what might be environmentally acceptable, what might be sustainable, given that we know everything, the riverbed is very dynamic and changing. So yeah, that's the brief in a nutshell. In terms of where the study's at, we kicked it off a couple of months ago with a workshop discussion to thrash out the questions, and the consultant is now working to pull that together into a technical report, which we'll share, of course, as soon as it's available, and get together to look at what it means for everything.
Thanks, Tim.
Can I add just one thing? Part of the brief is to look to some of the options that were discussed at the last engagement session we had in Glenorchy, Nepal. We had some people telling us, you could put flood banks here or do that. Those options being also part of this investigation that Dam Watch is doing.
Thanks, Jean-Luc. We've got a couple of questions there from Bill and Bob that I think are probably better asked in depth on the website, both because we're running short of time, but also because some of this stuff, we're putting these findings on the table fairly soon after we've had them come to be reported. So I think it's really important some of these detailed questions we get back to you with absolute detail. Some of that discussion involves talking to our partners, QLDC, and doing a bit more work. So again, it's not trying to dodge it. It's just making sure we give you some definitive answers. I just want to say thank you to, we'll close off the questions there. Again, happy to take any questions. There will be, you can either call the 0800 number, 0800 474 082, or you can email us at heatherofthelake@orc.govt.nz. If you do not get the newsletter, please provide your email address to us, either via those details that Fred has just put into the chat, or by emailing us, or by putting your email address into the chat. This information and a recording of this meeting, all the frequently asked questions that we've got to date, will be up on the website tomorrow, and that includes the reports themselves. The frequently asked questions are going to be a responsive thing. So if you have a question that you don't see answered, please let us know. Understand we haven't answered all the questions, so we will endeavour to do that as much as we can. So what I'll do now is throw over to Alexa to close with a karakia and potentially a couple of statements.
I won't take up any more time, so I'll just go into a karakia, but except to say thank you very much, everybody, for coming, and please do get your questions to us. Unahia ki te uru tapanui, kia wātea, kia māma, te nākau, te tinana, te wārewa I te aratakata. Koia rā e rongo, whakaerea ake ki runga, kia tīna. Hui e tai ki e. Kia ora. And good night, everybody.